In 2005, Discovery Channel released the documentary Alien Planet. The setting was a nearby habitable planet called Darwin IV, which was being explored by probes from Earth in the late 21st century. This was based on the book Expedition by Wayne Barlow, published 15 years earlier. Darwin IV is located in a binary star system 6.5 light-years from Earth, orbiting the larger of the two stars. Now, we come to the first problem with the scenario, the location of the star system. There is a binary star system 6.5 light-years away, known as Lumen 16, but these are brown dwarfs, i.e., they do not emit enough light to heat the planet sufficiently for liquid water to exist on the surface. The closest binary star system which could possibly support life is Alpha Centauri, which is also the closest star system to us overall. Well, okay, I guess it's technically a trinary system, but the third star, Proxima Centauri, is so far away from the main two that it would look like any other star in the night sky when viewed from the center of the system. After Lumen 16, the next closest binary star systems are Sirius, Gliese 65, and Procyon. But after Alpha Centauri, the next multiple star system with two sun-like stars is 61 Cygni, 11.4 light-years away. The orbital period of Darwin IV around its parent star is given at 728 Earth days, implying its sun is more luminous and thus more massive than ours. Both stars in 61 Cygni are smaller than our Sun, while Alpha Centauri A is larger, so the star system depicted in Alien Planet is most similar to Alpha Centauri. So, they may as well have made the setting Alpha Centauri. Now, onto the planet itself. It's a bit smaller than Earth, with a surface gravity of 0.6 Gs. The atmosphere is said to be twice as dense as that of the Earth at sea level, and is so oxygen-rich that it's toxic to humans. While we need oxygen to survive, at a partial pressure above 1.4 atmospheres, it becomes toxic, implying that oxygen constitutes at least 70% of Darwin IV's atmosphere. This quote-unquote oxygen-rich blanket is said to have been the result of the planet's oceans drying up. While not explicitly stated, this is likely from the loss of water to space. Earth's magnetic field protects its atmosphere from the solar wind, but as soon as it shuts down, the charged particles will bombard the upper atmosphere and split water vapor molecules into their constituent atoms, that being hydrogen and oxygen. The lighter hydrogen atoms fly off into space, while the heavier oxygen atoms recombine as diatomic oxygen. Although, if you give it enough time, eventually the oxygen will either be blown off into space too, along with other gases such as nitrogen and argon, or oxidize chemicals in the crust, leaving only a wisp of atmosphere remaining. This is what astronomers think happened to Mars, hence its thin atmosphere and red color. So, it's likely Darwin IV is also undergoing this process, and within a few hundred million years, the removal of most of its atmosphere will result in its multicellular life going extinct. But, without a magnetic field, wouldn't harmful radiation hit the surface, rendering much of it uninhabitable? Well, even without a magnetic field, before the atmosphere is eroded away, it could still shield the surface. To get an idea of what would be enough, we can look at the radiation doses one would experience on Venus at different altitudes. Venus has a thick atmosphere, but no magnetic field, so it's the best analog. Since the atmospheric pressure one would experience on a given planet is the mass of air above them times the surface gravity, if two planets have the same atmospheric pressure, and one has half the gravity that the other does, that planet will have twice the mass of air above each square meter of its surface. Because Darwin IV's surface pressure is twice that of the Earth, its surface gravity is 60%, and that of Venus is 90%. If one were at an altitude in Venus's atmosphere, where they'd experience 3 atmospheres of pressure, there would be the same mass of air above them as there would be if they were standing on the surface of Darwin IV, and thus be protected by a similar degree of radiation shielding. In the Venusian atmosphere, this pressure exists about 42 kilometers above the surface. At this altitude, one would be subjected to 0.008 microsieverts of radiation per hour. To put that in perspective, on the surface of the Earth, you're exposed to 0.1 microsieverts per hour. So, it does seem that so long as it's there, the thick atmosphere of Darwin IV would provide adequate protection from harmful radiation. Now, onto the ecology and organismal biology of the planet. Shortly after landing, the probes encountered an animal-like alien known as the Aero tongue. It is bipedal without arms, vaguely resembling a dinosaur, and appears to be an apex predator, and it principally relies on sonar to hunt prey. It's also a liquivore, meaning that instead of biting off chunks of flesh, it injects its kill with digestive enzymes and sucks up their liquefied flesh. But would this be a likely feeding strategy? On Earth, spiders have to liquefy their kill before consuming it. However, they don't inject their prey with digestive enzymes. Rather, they regurgitate these enzymes on them. Furthermore, spiders don't solely rely on their digestive enzymes to liquefy the remains of their prey, also utilizing mechanical shredding by their fangs, or chelicerae. Meanwhile, we see no other mouthparts on the Aero tongue. Well, I guess it does have the tongue, but it wouldn't be as good at this as the rigid chelicerae of spiders. That said, given the diversity of spiders, it could be argued that a vaguely similar feeding style would be viable on another planet. But at large sizes, it would be more difficult. When you inject prey with digestive enzymes to liquefy it before consumption, you will rely more on diffusion to spread the digestive juices, enzymes and acid throughout the body. On a small animal, these will spread through the carcass in a much shorter time frame, and in the subfield of behavioral ecology, time is a valuable thing. While a predator is waiting for a kill to digest, another predator could come along and steal it. You might argue that since the Aero tongue is an apex predator, no one else would challenge it. But other predators can come in packs, or a larger member of its own species could do so. On top of this, by the time it stole the kill, the carcass would already be partially liquefied, meaning the thief could start eating and it wouldn't have to expend its own digestive enzymes. Enzymes, being proteins, are valuable resources, and to give an analogy, many venomous snakes will give dry bites when biting in self-defense, since venom is also made up of proteins. Meanwhile, if a predator immediately starts tearing chunks of flesh off a kill and consuming them, if it gets chased off it a little while later by another predator, it will at least have gotten something off it, which it will digest while sulking, on top of not having done the thief any additional favors by pre-digesting the carcass. So, I would say that such a feeding strategy is unlikely. But what about the use of sonar to locate prey instead of relying on eyesight? Again, this seems unlikely. On Earth, eyesight evolved many different times, and while sonar did as well, it only came about after the use of eyesight had been the status quo for hundreds of millions of years. This strongly implies that the use of eyesight is more advantageous than sonar for most organisms. There are of course exceptions, such as bats and whales, but they live in conditions which greatly decrease the usefulness of light as a means of detection. With bats, there's little light at night, and with whales, it doesn't travel very far in the water, and sound travels faster and farther in the water than it does in the atmosphere. Bat sonar can detect prey only a few meters away, and larger objects like trees at a distance of a few hundred meters, while our fairly mundane eyesight can see kilometers away under good conditions. The use of sonar, an active means of detection, also conveys a heavy risk of giving away your position to either prey or predators. There's even reason to think that using sonar would be even less advantageous to life on Darwin IV than it would be here on Earth when compared to eyesight. Our planet has one sun, while Darwin IV has two, which it orbits in an S-type. This means that for half of the year, the star it doesn't orbit will be visible in the day, and for the other half it will be visible at night, during which time the light intensity at night will be comparable to the Earth at dusk. At such an illumination, most animals can still rely on eyesight, making it even more useful on such a planet. All this to say that the use of sonar by the Aero tongue, and most other animal-like aliens on Darwin IV, is very improbable. And if that wasn't odd enough, the Aero tongue also has bioluminescent patches on its body. Organisms on Earth use bioluminescence for a variety of purposes, but the two most common are luring prey and communication. For both these scenarios, the other animal has to see the patch, and this won't happen much since most animal-like organisms on Darwin IV have poor to non-existent eyesight. To make matters even worse, the Aero tongue has its patches illuminated in broad daylight. Bioluminescent animals here on Earth use it in low-light conditions because their light will stand out more, while it would be barely noticeable with high ambient light levels. Since producing light requires metabolic energy, and the Aero tongue wouldn't be getting anything out of it, the behavior would be incurring a cost for no benefit, and thus be selected against. The Aero tongue then chases a herbivore called the gyrosprinter. This one has its two front and two rear legs fused, implying it evolved from a quadruped. This seems fairly plausible, since we often see animals possess body parts that came about from the fusion of others in its ancestors. But the subsequent chase scene is a bit problematic. The gyrosprinter manages to evade the Aero tongue by rapidly swerving. But the Aero tongue has two appendages which look like a cross between a tail and a wing sticking out from the sides of its hips, and oddly enough, it doesn't utilize them to maneuver, i.e., extend the one on the inside of the side it's turning to so it can act as a counterbalance, which would in turn allow for a tighter turning radius without falling over. You could say that perhaps the Aero tongue skeleton couldn't withstand the G-forces without snapping, but it's stated that the creature is an ambush predator, implying that its skeleton is able to withstand the rapid acceleration associated with an ambush. The next day, one of the probes, Ike, explores a forest of what's known as plaquebark trees. These are supposedly photosynthetic like trees here on Earth, but they don't appear to have as many leaves. Such structures are important because they increase the surface area over which light can be absorbed. It is true that on Earth, water versus light is usually what limits terrestrial plant growth, but most of their water comes in the form of rain, which has sudden pulses of abundance. So, if plants had fewer leaves and it suddenly rained, their growth would quickly become light-limited. But on Darwin IV it hardly ever rains, and these small pocket forests are sustained by underground aquifers. These will provide the pocket forests with a much more steady supply of water, negating any advantage that having a large quantity of leaves would give in terms of being able to capitalize on a sudden increase in the availability of water. In this situation, having as many leaves as plants on Earth would probably be a hindrance, because being soft and tender when compared to the rest of the plant, leaves are an easy target for herbivores. So, I would say these kinds of trees are pretty likely on such a planet. We also see large fungi-like organisms growing on the forest floor. While such fungi are non-existent on Earth today, between 420 and 360 million years ago, there was a fungi known as Prototaxites which grew to 8 meters in height, towering over contemporary vegetation, meaning fungi analogues like the giant Darwin tomatoes are entirely possible. The other probe, Leo, finds a herd of creatures called Unths, named after their vocalizations. These have a similar build to the Aero tongue, with a dinosaur-like shape, 2 toes, and bioluminescent patches. This suggests a recent common ancestry between the two, but Unths are herbivores, living a lifestyle similar to buffalo here on Earth, with tusk-like structures instead of horns. Leo then hears a series of calls similar to that of the elk. We then see 2 creatures known as bladderhorns headbutting. These inflate antler-like appendages to produce their vocalizations, and also include bioluminescence in their display, and even if they, like most other Darwinian creatures, have poor eyesight, the bioluminescence would be plainly visible at close ranges. So, this is one of the most feasible uses of bioluminescence we see in the documentary. Then, Leo is attacked by a mysterious creature, and we go back to the probe Ike. The probe is exploring another pocket forest, where it finds a creature known as the Daggerist. This is an arboreal alien which glides from tree to tree with flaps of skin and climbs them with pick-like claws on its forelimbs, hence the name Daggerist. This creature preys on a nectivore called the trunksucker, and, like the Aero tongue, it's a liquivore, using a hardened tip at the end of a long tube to inject its prey with digestive juices and slurp up their remains. The Daggerist has an external skull which closely resembles that of the gyrosprinter, suggesting that the two share a recent common ancestor, like the Aero tongue and Unth. We also see the gyrosprinter extend a long tongue from the bottom of its head, which could be homologous to the feeding appendage of the Daggerist. Ike ventures further away and finds a patch of moss with several mounds that have saplings growing on them. These begin to shake and turn out not to be mounds at all, but huge creatures known as grovebacks. These aliens stand a colossal 5 stories high once they emerge, and it's said that they are not hibernating in the ground, but feeding, and once the soil is depleted, they move to a new location. Now, how could they quote-unquote feed on the soil? Well, they could absorb nutrients and organic matter through their skin, but they could only get it from a centimeter or so away from said skin. One way to maximize the absorbance of anything useful in the soil would be to grow microscopic hair-like structures into it, which would resemble fungal hyphae. The groveback would then shed and or reabsorb these when it moves to a new location. But would animals that big be possible, on land at least? Well, the largest land animal in Earth's history is Argentinosaurus, which weighed in at 85 tons and stood 7.3 meters at the shoulder. Should this represent the upper size limit of a land animal, creatures on Darwin IV should be able to grow to 12.2 meters at the shoulder and weigh 394 tons. The groveback stands 15.4 meters at the shoulder, which at first would make it seem impossible, but that's assuming Argentinosaurus did hit the upper size limit of a land animal. A modeling experiment suggested that Argentinosaurus did indeed hit the upper size limit for a sauropod dinosaur, but larger animals were possible with some remodeling. So, did the groveback have an overall geometry that would allow for a greater mass? In short, no. For one, it has a rear keel which it has to drag around, and sprawling legs, while straight column-like legs are needed to support heavy weight, making this alien pretty improbable. James Kirkland argued that they would have to be much less dense than life on Earth, but with the way they're built, the grovebacks probably couldn't exceed the aforementioned 12.2 meter height limit. Ike then goes on to explore the littoral zone, where he finds a herd of creatures known as littoralopes. They appear to be herbivores, and have a tail which closely resembles their head. This is most likely to confuse predators, who would quite often end up attacking their tail versus their more vulnerable head. This strategy is employed by some lizards here on Earth. One issue I've noticed with the littoralope and many creatures on Darwin IV is the lack of insulation. Most appear to be quite active, implying a warm-blooded or endothermic metabolism, and the ambient temperature upon the probe's arrival is given at 70 degrees Fahrenheit, or 21 degrees Celsius, and we also see snow from time to time, implying the temperatures regularly get much lower. At such temperatures, pretty much all endothermic animals here on Earth, birds and mammals, employ some kind of insulation to minimize heat loss. So, it would make sense that the creatures on Darwin IV would also do the same. In the book Expedition, there are some aliens on the planet which live in the polar regions, and these insulate themselves with a blubber-like material. Yet, they live on land, and there's a good reason endothermic animals which live in the water employ blubber, while those on land employ, shall we say, fluffy insulative material, that being fur in mammals and feathers in birds. The quote-unquote fluffy insulation works by trapping pockets of air close to the body, which slow down the rate at which heat escapes into the surrounding air. With the majority of their volume being a gas, fur and feathers require less mass to provide a given amount of insulation than blubber would. But as soon as you go into the water, the spaces in the fluffy insulative material get waterlogged, negating its effect, but this isn't the case with blubber. You could argue that animal-like organisms on Darwin IV had yet to evolve such insulative structures, but in both the lineages which led to birds and mammals, the evolution of insulative structures seems to have been tied to the evolution of endothermy itself, and, since this happened independently in both, it would be more likely that alien life would evolve fur and feather-like structures as they evolved in endothermic metabolism. I think part of the reason that sci-fi and spec-evo world builders don't use these and instead make most of their aliens naked is because doing otherwise would make the aliens look more like birds and mammals, animals we're very familiar with, and thus make them seem less alien. We then see two flying creatures with 15-meter wingspans swoop down on the literalope herd. Instead of using a flapping motion to fly, these skewers combust methane in 4 jet-like pods. These appear to have a principally ramjet-like function, or using the forward motion to compress air for combustion in the engines. Is this really realistic? Well, on Earth, we've built unmanned ramjet planes, but because ramjets use forward motion to compress the air, they can only produce sufficient thrust to fly at Mach 0.5 or above. This comes out to 172 meters per second, while the top speed of the skewer is given at 245 meters per second. Although it should be noted that while ramjets will fly at this speed, they reach a maximum efficiency at Mach 3, or 1029 meters per second, and are very inefficient at subsonic speeds, making something like propellers, or flapping wings in the case of organisms, in such situations more advantageous. Although, the partial pressure of oxygen in Darwin IV's atmosphere is 7 times greater than on Earth, and it makes up a larger percentage of the air, which should in turn make ramjets more efficient at lower speeds. But I'm not exactly sure how this correlation works, and it could be more efficient than flapping in Darwin IV's atmosphere. If there are any aerospace engineers watching this who can provide some insight, please write it in the comments. But even if a ramjet was viable on Darwin IV, it, like all jet engines, will produce engine temperatures in excess of 2000 degrees Celsius. This would burn any kind of biomolecules, meaning the skewer would have to biomineralize their engine chambers. Materials used in biomineralization here on Earth, such as calcium phosphate, silicon dioxide, and calcium carbonate, can't withstand these temperatures, but dolomite melts at 2,800 degrees Celsius, so it could be used to surround the chambers. However, it would have to be in contact with flesh in the surrounding wing, and it would end up singeing it. This could be mitigated by making the dolomite shell thicker, but this would probably make the skewer too heavy to fly. So, I'd say their mode of locomotion is impossible. The skewers also use echolocation, and appear to have a rounded melon-like structure on the top of their head. Whales use their melon to focus sonar clicks in a certain direction, and it may be that the skewers do the same. However, the skewer's use of sonar is arguably the most improbable of all animals on Darwin IV. This is because they move at a sizable fraction of the speed of sound, meaning that the sound waves move slower relative to the skewer and are even less useful at long ranges. But the biggest problem with sonar at this speed has to do with the Doppler shifts. Echolocating animals use specific sound frequencies, but if your range of speeds is at a large fraction of Mach 1, the Doppler effect will alter the frequencies as your forward motion compresses the sound waves, increasing the frequency. This is made worse when said forward motion increases the rate at which you receive the returning sound waves from the echo, meaning the echoes the skewer receives won't be of the frequencies its ears are adapted to use in echolocation. Detecting prey at long ranges is the reason birds of prey are the most long-sighted animals on Earth, and if there's a creature on Darwin IV who should use vision instead of echolocation, it's the skewer. The skewer is also a liquivore, but instead of injecting prey with digestive juices, it impales it on a lance and drains its fluid, and to maximize how much they can get, the skewers hunt in pairs, passing the kill from one to the other until they've drained all the liquids that they can. While for previously discussed reasons, liquivores being the dominant predator isn't exactly likely, there is a scenario where I think it could work. Perhaps tens of millions of years ago, the ancestor of Darwin IV's dominant predators were one of many, most of which consume flesh like large predators do on Earth. But then a mass extinction hit, wiping out these other predators. Meanwhile, the ancestor of Darwin IV's modern predators had anatomical and physiological attributes that allowed them to fill the apex predator niche after the extinction, even if their feeding style wasn't ideal for this role. The extinction itself could have been caused by climatic upheaval that co-occurred with the disappearance of the planet's oceans. After the literal lobe carcass is left on the ground, scavengers called jet darters fly on it and start consuming. Yeah, I'm going to go out on a limb and say that these aren't possible either. Later, some of these are flying through what appear to be a field of mushrooms, but these end up zapping them. These mushrooms are likely connected to an underground network of roots which composes a single organism, which uses electricity to kill its prey. There are organisms on Earth which use electricity to hunt, such as the electric eel and electric catfish. So, at first, these mushroom-like organisms may seem plausible, but there's a key difference. The fish live in water, which is a much better conductor than air. In order for electrical arcing, or a spark, to travel between 2 points in air separated by 1 meter, the difference in electric potential between them would have to be 3.4 million volts. To put that in perspective, the electric eel can only produce 600 volts. I can't say for sure if it would be impossible for an organism to generate the voltage required for electrical arcing to go through the air, but there isn't even a remote precedent for it in Terran life. Next, we see a gyrosprinter being stalked by a group of predators called prongheads. These have the same dinosaur-like shape of the arrow tongue, again implying a close relationship. I think we should take a second to see how the creatures of Darwin IV could be related to each other. The theropod-shaped creatures, the arrow tongue, uinth, and pronghead, could be said to form one clade, while the gyrosprinter and daggerist form another. But, as discussed before, it's also likely that the major predators of Darwin IV are part of a single clade, linking the two branches, implying that the uinth and gyrosprinter evolved herbivory independently. Given that other herbivorous creatures like literal lobes are quadrupeds, it's likely the ancestor of this clade was also a quadruped. So, we can use them as the outgroup to root our phylogeny. There's only one way the daggerist and gyrosprinter would fit together, but what about the theropod-like members of this clade? Is the uinth, pronghead, or the arrow tongue the outgroup? Well, given that the arrow tongue and the uinth have hoof-like feet, while the pronghead has clawed 3-toed feet similar to the hind limbs of the daggerist, and these are on opposite sides of the tree, it's likely that the common ancestor of the clade had such feet, while the common ancestor of the uinth and arrow tongue had the hoof-like 2-toed feet. The uinth and arrow tongue both also have a wedge-shaped head, further implying a close relationship. On the theropod-like branch of the phylogeny, the progenitor would have lost its forelimbs after evolving a bipedal mode of locomotion. It also would have had a 3-bladed head similar to that of the pronghead. In the branch that would give rise to the uinth and arrow tongue, the top prong was lost, and in the uinth, the lower 2 prongs became its tusks as it evolved herbivory. Now, the skewer is also part of the liquivore clade, but it's hard to get an idea of where it fits into the family tree. Given that it flies while the Daggerist glides, one might be tempted to think that the two would form a clade together, but this isn't a strong case for it, since we see gliding evolving many times on Earth. The next place Ike visits is the Amic Sea. As Darwin IV's oceans dried up, unicellular organisms formed a huge colony which covered the entire surface and later the whole depth of the remaining ocean, forming a gelatinous superorganism. On Earth, there are organisms such as cyanobacteria, most notably Nostocales, which will secrete polysaccharides, which form a gelatinous substance when it comes in contact with water. It does this to retain water in semi-arid environments to minimize evaporation. So, there is some precedence for the Amic Sea on Earth. However, forming such a gelatinous colony in a puddle is one thing, but doing so in an entire ocean is another. While there are microbes who use such methods to store water, many times in Earth's history, enormous bodies of water had dried up, most notably the Mediterranean during the Messian salinity crisis, although it later refilled. But when these bodies of water dried up, we never see any organisms forming anything that remotely resembles a superorganism such as the Amic Sea, even in ponds. I'd say an Amic Sea is pretty unlikely. One major hindrance is probably herbivores who would consume such biofilms as they formed, or at least before they got big enough to cover the whole body of water. Even if increasing salinity levels killed off herbivorous marine creatures, there would still be semi-aquatic ones who would venture into the water and consume the microbial colonies. And we do indeed see Darwinian fauna consuming the Amic Sea, most notably the 22-meter-tall emperor sea striders. This creature has a pair of mouths on each of its feet, which it uses to consume bits of the Amic Sea with each step. Like the groveback, it's far too large to be mechanically feasible if it had a density similar to life on Earth, which is pretty similar to water. In fact, it would be even harder for the emperor sea strider to stand, because not only does it have sprawling legs, they don't even appear to have rigid internal support structures, i.e., bones. Because of this, I think that not only would the sea strider have to have something like internal gas-filled chambers, they would have to be filled with hydrogen and be large enough to provide a buoyant force at least half of the weight of the creature. And if I were to guess, I'd say probably it's more like 85% of its weight. We see flying juvenile sea striders, and while these have wings, they're too small to allow for flight on their own, implying that they also use a lifting gas to fly, further reinforcing this hypothesis. But if this is the case, how do the sea striders prevent themselves from falling over in a windstorm? My guess is that they employ suction at their feet mouths to keep them bound to the surface of the Amic Sea, and they have most of their air sacs in their torso, putting their center of gravity closer to the sea. The last scene involves Ike finding out what knocked out Leo, and it turns out to be a quasi-sapient creature called the Eosapien. This animal floats, employing entirely lighter-than-air flying, with gas bags filled with methane. While it's the only lighter-than-air flying creature portrayed in Alien Planet, except possibly the sea strider nymphs, there are other such creatures on Darwin IV and Expedition, namely the Rugose floater and the ebony blisterwing. Lighter-than-air flying creatures are commonly discussed in Spec Evo, but are they feasible? Well, flight evolved many different times independently here on Earth, and every time it used heavier-than-air methods. This strongly suggests that lighter-than-air flight is either unviable or at the very least unable to evolve on a planet like Earth. You could argue that no animals have the means to evolve it, but many do have cavities filled with gas, which organisms such as the nautilus do use for buoyancy purposes, and many have bacteria which produce hydrogen as part of their microbial flora. Yet, no one has ever put two and two together to evolve lighter-than-air flight, further indicating it's just very disadvantageous, or at least compared to heavier-than-air flight. Now, why is this? Well, we can only speculate, but one hypothesis is that they just get thrown around in the wind and slammed against a sharp object. But I think a more likely explanation is that lighter-than-air creatures would just be too vulnerable to predation by carnivorous heavier-than-air flying creatures. One could imagine that if a jellyfish evolved the ability to float in the air, an eagle could easily puncture its buoyancy cells with its talons. But that's Earth. What about Darwin IV? Could lighter-than-air flight be usable there? Well, let's crunch some numbers with basic physics. Say we have a lighter-than-air creature with a volume of 1 cubic meter. The buoyant force on this volume, 1, multiplied by the fluid density, air at sea level is 1.225 kilograms per cubic meter, multiplied by the acceleration due to gravity, 9.8 meters per second squared, gives us a buoyant force of 12.005 newtons, which would provide enough force to lift a 1.225 kilogram creature. But that wouldn't be the weight of its biomass. You also have to account for the mass of the lifting gas. Let's say you use hydrogen, which has a density of 0.083 kilograms per cubic meter. However, to keep the gas bladder inflated, the gas inside would have to be kept at a greater pressure than the surrounding air. Let's say it's twice as high, which would give the lifting gas a mass of 0.166 kilos, leaving 1.059 kilograms to constitute the organism's biomass. Now, how would such a creature fare on Darwin IV? Well, since the atmospheric density is twice that of the Earth at sea level, 2.45 kilograms per cubic meter, and it has 60% of its gravity, 5.88 meters per second squared, a 1 cubic meter gas bladder would provide 14.4 newtons of force, which in Darwin IV's gravity could hold a 2.45 kilogram object in the air. But again, we have to account for the mass of the lifting gas, and let's say it's again hydrogen. Kept at twice the ambient atmospheric pressure, it would be able to lift 2.118 kilos of biomass. Although the Eo sapiens are said to use methane, which could only lift anything if it was held at a pressure 1.86 times that of the surrounding atmosphere or less, so their air sacs wouldn't have been large enough for them to float. That aside, these calculations, on their own at least, seemingly suggest that lighter-than-air flight would be more feasible on Darwin IV than on Earth. But evolution doesn't work in isolation, and we also see heavier-than-air flyers on Darwin IV. The equation for lift a wing would provide is the velocity squared times the lift coefficient, which is determined by the geometry of the wing, times the atmospheric density. So, the thicker atmosphere would also make it easier for heavier-than-air creatures to fly. There is also the factor of the lower gravity. With less gravity, both lighter and heavier-than-air flight methods would have to provide less lift to get a given mass airborne. But lower gravity will also decrease the buoyant force, i.e., such an environment would be advantageous to a heavier-than-air flyer, but not a lighter-than-air one. So, if predation by heavier-than-air carnivores prevent animals from evolving lighter-than-air flying methods, it would be even less likely on Darwin IV. If any world builders out there want to make a planet where lighter-than-air flight would be more advantageous, it should have a higher gravity, since this negatively impacts heavier-than-air flyers and doesn't impact lighter-than-air ones, and a heavier atmosphere. And by heavier, I don't mean denser. I mean one whose constituent air molecules have a greater molecular weight, increasing the difference in density between the surrounding air and that of the lifting gas at similar pressures. The Eo sapiens throw spears, implying they have begun tool-making. In other words, they have entered their version of the Paleolithic. Regretfully, the documentary ends when the Eo sapiens destroy Leo. Seeing a disk the probe launched is a threat, and we don't get to learn much about them. But in an interview, Michio Kaku argues that if we find intelligent life, it will likely be a predator, because while the fox has to stalk the rabbit and figure out the right distance to pounce, the rabbit only has to run. However, this is a gross oversimplification of animal behavior. Herbivores also have to forage, which can often be tricky and require problem solving. Indeed, when we look at the animal kingdom, we find many brainy herbivores. Some of the most notable of these are elephants and horses. Also, some of our closest relatives, the great apes, are herbivores. Chimps are known to dabble into carnivory, and were long thought to be the smartest non-human apes. However, this doesn't seem to be the case, and that honor goes to the orangutans, who are herbivores. Also, on the avian side, there is a long-standing debate as to whether the smartest birds are parrots or corvids, with parrots being almost exclusively herbivores, while corvids are omnivores. So, yeah, it doesn't appear that carnivory is a good indicator, let alone a prerequisite for sapient levels of intelligence. Now, as for the documentary as a whole, one way world builders often try to make alien worlds feel grounded yet truly alien is to have the dominant organisms use locomotion and feeding styles not used by organisms which fill similar niches on Earth, yet are used by some other animals. But this assumes that which strategy is employed by creatures which fill a niche, liquivorous feeding versus solid food, using sonar versus sight to get around, and employing lighter versus heavier than air flying methods, is only that way because the organism happened to have it when it first occupied said niche. In reality, certain strategies simply work better for filling given roles in the environment, and animals didn't come to fill their niches by chance. They do so because their features were the ones most advantageous for occupying it. All of this will be applicable to extraterrestrial biomes, because while the players are different, the laws of survival are the same. As always, if you enjoyed what you saw, please like and subscribe, and share this video with friends. Thanks.